So what we're going to cover today is the probability of two or more events occurring. And what we want to make sure you understand is a couple of definitions and concepts, which will be a little bit easier to understand once we go through some examples. So the first two definitions are what are called mutually exclusive and not mutually exclusive events. Okay? And mutually exclusive means two events that cannot occur at the same time. I'm going to give you the formula. Not that you really know how to know the formula, but it's easier if you understand. So the probability of A or B happening, and we actually did a little of this already, is the probability of A happening and the probability of B happening. Okay? So, for example, the probability that I roll a 3 and then roll an even number. Okay? Not a reven. Or roll even. Well, the probability that I roll a 3 is 1 out of 6. The probability that I roll an even number is 3 out of 6. So that combined probability, it's a 6 out of 4, is 4 out of 6. Okay? Now, not mutually exclusive means where you can have an overlap. And when you see the example, should be very clear. So it's a very similar probability, except I have to subtract out when A and B can occur. So let's say I want the probability of rolling a prime number. And again, what we're talking about is a six-sided die. Well, the probability of rolling a prime number is 3 out of 6. And the probability of rolling an odd number is also 3 out of 6. But I have an overlap. I have 3 and 5 that are in both of them. So I have to subtract 2 out of 6 to get my 4 out of 6. Now, quite honestly, do you have to do it in this fashion? No. You can list out what the possible events are. All right, so if I'm rolling a six-sided die, so I have these numbers, and I want the probability I'm going to roll a prime or an odd, then I know it's 1, 2, 3, and 5, and stop there. But we just want you to understand how that works. Now, the more relevant is the concept of independent and dependent events. And for probability, it actually revolves around a very simple concept and examples. So an independent event is when the first event has nothing to do with, or has no impact, I should say, on the second event. So in other words, the simple way to do it is if I were to remove a marble from a jar or draw a card from the deck and then put what I drew back in, then my first event has no impact on the second. A dependent event is when the first one impacts the other. So now going back to our example, I draw the marble or draw the card and I don't put it back in. Now we know that it has an impact on that event. Okay? All right. And then you can read here our example with drawing the fruit. All right. So I have an urn, which is a jar, that contains 3 red and 5 white marbles. A marble is chosen at random, and it is replaced. Okay? And what that simply means is it's put back in. So what's the probability that they are both red? The first one being red is 3 out of 8. Since it's put back in, it's still 3 out of 8. So it's 9 out of 64. What's the probability that they are both the same color? Now you got to take a look here for a second, because I have 2 possible scenarios. One is it's red, red. Well, we just did that before, which is 9 out of 64. Or the other one is the probability that it's white, white. And that is 5/8 times 5/8, or 25 out of 64. And when I add those, and I want to make didn't mean to make my division bar so large. That's what I wanted. It's 34 out of 64. Okay. Now, let's go to the next example where it is not replaced. So that means the marble is taken out and kept. So the probability that they're both red, it's the first probability is the same, but now everything reduces by 1 because the assumption is that the marble you chose was red marble. Okay? All right? Now, probability that one is red and one is white. Well, the first probability, since it doesn't tell me, is I could have gotten a red and a white. So 3/8 times 5/7, which is 1556. Or could have gotten white and then red, which is 5/8 times 3/7, which is the same 1556, which in total is 30 out of 56. Okay. All right, we have Scott with his 2 navy and 4 black socks. What's the probability that he pulls a matching pair if he pulls 2 of them? Well, what is it? He could have pulled N, which is 2/6. That's a pretty poor looking 2. 2/6, and then 1/5, which is 2/30. Or he could have pulled 2 black, which is 4/6, and 3/5, or 12/30, for a total probability of 14 out of 30. Okay? It clearly makes sense that the probability of 2 black is higher because there are more black socks. All right. A card is selected from a deck and it's not replaced. Probability of both are black. 26 out of 52 times 25 out of 51. And when you do the multiplication, 650 over 2652. Okay? Probability that they are both spades. 13, 12, 156 out of 2652. And then both are aces. 4, 3, 12 out of 2652. Okay, so again today what we covered was a situation where we had independent and dependent events, mutually exclusive, non-mutually exclusive, when factoring out our computing our probability of something happening.